Hello, everybody, and welcome to the Cosmos Show, a place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here you can pick the brains of astrophysicists, get some advice from a space doctor, learn what astronomers have to say about life, and find out what's happening up above your head, all in the same place. So join us every other Tuesday live at 6 p.m. Mountain Time on Twitch, YouTube, and now Facebook. So welcome to all of our Facebook guests for our first live streaming there. And remember, you can chat your questions, or you can give us a call using your Zoom application at 929-205-6099. And the meeting ID should be displayed on your screen for joining us. So on this week's show, we have Claire Gorman, a PhD student in astrophysics at the University of Cambridge, who studies exosolar planet landscapes. So we're very excited to chat with her later on. But before we welcome Claire, let's welcome our co-stars. First, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy. It's Nora Bailey.
Hey, everyone.
Hey, Nora. Welcome back.
Thanks.
Next, the Deputy Director of Education and Public Outreach at the Vera Rubin Observatory. It's Dr. Lauren Corleys.
Good to see everyone.
Good to have you back, Lauren. Next, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi there.
And last, but certainly not least, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hi, everybody. Good to be here.
Good to have you, Danny. Welcome back to all of our three co-stars who weren't with us last time. We had some great fill-ins for you, but it is awesome to have you all back. So thanks for being here. All right, so let's go to Astro Advice. So our quote this evening comes from one of the history of astronomy's most famous women observatory, astronomers, Annie Jump Cannon. And what she has to tell us this evening is that a life spent in the routine of science need not destroy the attractive human element of a woman's nature. And not what I was expecting from Annie Jump Cannon, but I thought it was a provocative quotation nonetheless, especially as a follow-up to our conversation last time with Dr. Nicole. And so, curious what folks think about this, and the sky is not the limit. So I'll leave it at that. What do you think?
I love it.
Well, then maybe it's a question for you, Nora. I'm not entirely sure what she means by the human element of a woman's nature. Like, what does that mean to you?
I guess I was thinking more the attractive human element of a woman's nature, because I feel like
I left out the important word.
I'm thinking not so much in astronomy, but especially when I was in the military, and maybe Danny might have similar experiences, but there is this really common refrain that women who are in those spaces are not attractive. We are somehow losing our womanhood or whatever, and that we don't count anymore. Like, we don't count as attractive, desirable women. And I think that's BS. And so, way to go, Annie Jump Cannon. I totally agree. This is not an either or thing. I saw someone the other day that said, someone accused me, this was my quote, someone said this, they're like, someone accused me of being a space Barbie. And I was like, thank you. That's exactly what I set out to do. And I was like, I love it. So I think it's great.
Excellent. Thanks, Nora. Lauren, what about you?
Yeah, I think sort of along the same lines of there is humanity in science. We like to think of it as this sort of like logical, like devoid from emotion, but like none of that is true. It is this pursuit where you can like feel a lot of things and express creativity and like actually be a human who pursue science and not just this like robot who is doing things. And so that's what came to mind when I saw this quote, of like trying to make it fun and make it, you know, a thing that I want to be doing and not just calculating numbers all the time.
Scientists have emotions?
Crazy. I know, crazy.
Crazy.
You know, maybe we're missing one of the, because like one of the words in here is routine. So maybe the thing to pull from this quote is the concept of it being, you know, even though it the pursuit of a scientific, you know, of answers could be perceived as you know, a routine, or kind of, even though we know it's not mundane, somebody on the outside looking in might think, oh gosh, you're doing the same thing every day, you know, on a functional level, when, you know, when really it's a little bit more complex than that. I don't know, just a thought.
I like that. I mean, I think that's actually very pertinent to Annie Jump Cannon, because didn't she classify something like 300,000 stars or something like that over the course of her career, and, you know, basically is responsible for our, you know, modern day classification scheme in a lot of ways. So she definitely did a lot of routine work, but apparently also was really interested in maintaining her womanhood along the way, which is pretty sweet. Nick, did you want to weigh in on this one?
First read, it was looked like a early commentary on work-life balance.
Yeah, you know, it totally could be. I hadn't thought of it that way, but I do like that. Anything else? All right, well, let's get down to our next segment, Astro 365, this day in astrophysics history. So there was a bit of a discrepancy here when I was doing some research on this, because some websites claim that the Mars Spirit rover actually landed on Mars in January 3rd, which would have been yesterday, 2004. And other websites claimed that it landed on Mars on January 4th, 2004. And it turns out that it's all just about what time zone you are using to determine the landing time on Mars. So if you're using a Greenwich Mean Time on Earth, then it landed on the 4th. If you're using Pacific time, it landed on the 3rd. Who knows when it actually landed on Mars time. But sometime between the 3rd and the 4th in 2004 was the landing of the Mars Spirit rover in 2004. And another interesting thing that happened this month, January 1st, actually, was the day that Giuseppe Piazza discovered Ceres, the very first asteroid, in 1801. So just a couple hundred years ago, the very first asteroid on January 1st. Another interesting tidbit from January 5th was that the second largest dwarf planet in the solar system, Aries, was discovered in 2003 by Mike Brown and his colleagues.
It's the second largest, but it's the most massive, I want to point out.
Oh, that is very interesting.
Yes.
So just denser than Pluto? Nice. Yep. Very cool. I did not know that. Thank you for adding that tidbit in. And then also, Galileo discovered the 4 largest moons of Jupiter on January 7th in 1610. So just under 400 years ago. And if you don't already know, he used the orbits of those moons around Jupiter to realize that there were heavenly bodies that weren't moving around the Earth. These 4 moons definitely were moving around Jupiter, which led him to believe that the sun and the moon, or at least the sun, was not actually moving around the Earth either, but that the Earth was moving around the sun. So that led to a whole lot of trouble for Galileo. And that all started on January 7th, 1610.
So what you're saying is that it's a popular time of year to upend solar system classification schemes.
Yeah, nice connection, Nick. That seems to be the case.
All right, Planet 9, here we come any day now.
I know, right? Is there any news on Planet 9? I haven't heard anything in recent days. That's also a Mike Brown deal, right?
Well, yeah, he's the one instigating it, I'd say.
It sounds like you have an opinion on this. What do you got, Nick?
I just know about it because, well, yeah, so this is the theoretical planet that's disrupting some, I guess, or what would those be, comets or asteroids from the far reaches of our solar system.
Kuiper Belt, yeah.
Yeah, Kuiper Belt objects. And it's not a lot of them. So the statistics on it's maybe a bit of a reach, but then he's pretty good at what he does. So we could believe that. And one of the reasons I know about it is you've actually got cosmic microwave background telescopes looking at for it, because in the millimeter, it would probably be kind of bright. Except we're not really geared to look at things in the solar system. And so it's there's a couple people in our collaboration who've taken it upon themselves to write intriguing routines to basically shift all our images in these blind searches for some planet that might be out there. No luck so far, but we do have a bet going on when they'll find it.
Oh, what's the bet, and what odds are you giving? Where do you stand?
We usually bet on dates in our collaboration when things will happen. So I think we put placed bets on the Planet 9 press conference, and I think the range of dates was anywhere between a year or two ago, which obviously those people lost, and about a few hundred years out, because a few people just didn't think it was there.
And what do you think? Is it there, not there?
I don't know. You trust the distribution, right? I think that was in 5 or 6 years. So
I think the Vera Rubin Observatory will really help with this, not with direct observations, but I mean, part of the problem and the reason that there's been so much back and forth about is Planet 9 there, is it statistically significant, this clustering in the trans-Neptunian objects, because we just don't know very many of them. And I think once we get more with VRO, like that will really help nail these statistics. Because right now there's kind of an argument about whether these biases of the surveys that were used to discover these trans-Neptunian objects are imprinting some kind of false signal on the distribution.
Lauren, what do you think about that?
I mean, I totally agree. We're going to find way more of these objects by hundreds times more than what we currently know now. And the way the survey is set up is we don't point the telescope, it just looks at the sky all of the time. And so these biases of people choosing where to point or where to look are erased. And so we can actually get a sense of, are these things behaving the way that we expect them to or not? So we're definitely going to learn a whole lot more about the solar system in a few years. And one of the exciting things is that the asteroids are going to be some of the first science to come out of the Rubin Observatory, because they're moving across the sky. We'll find a lot of them within the first few years. So it's going to be some of the first big discoveries that we'll be making.
Yeah, and what do you think? Is it there or is it in?
I think you can infer a lot from a few data points. So I am not convinced, but I believe that the modeling that they're doing is correct to, the knowledge that they have. But
what is your desire? You'd like there to be a Planet 9.
Yeah, it would be fun. It's been a little bit sad ever since Pluto, got demoted. I feel very strongly about that one way or the other. If we brought Pluto back and then had 10 planets, that would also be fun. But I think it'd be neat. It'd be cool to find another one.
I mean, the real question is, if it does turn out to exist, will it have a name with the first letter P? So we can go back to the old mnemonic device of remembering the order of the planets. Right. So I guess if it's Mike's discovery, he's got to find a Hawaiian god or goddess that starts with the letter P. That's the way he seems to go, but that'll be interesting too.
There's always Pele, if that hasn't been used yet. So
ooh, there you go.
There waiting.
Hey, that sounds good. I love that as the name of a planet. Lauren, do you know much about Pele? Can you tell us about that?
Yeah, Pele is like the goddess of the fire and the lava. So the different lava things are referred to by her, and she's one of the spirits that motivates the eruptions, as far as I understand. That's a very simplified explanation of that. Anyone who is interested should definitely look up more accurate information.
Oh, that's cool. I love that as a name of a planet too.
And that's Pele spelled P-E-L-E?
That's right, yeah.
Okay, so also the world's greatest soccer player ever.
It's true, I've never made that connection. That's incredible. Brazilians will be happy.
They will indeed. Indeed. Well, speaking of asteroids or comets potentially being discovered by the VRBO or other telescopes, I can't help but bring up the movie that I just watched this past weekend, Don't Look Up. Has any of you
No spoilers.
No spoilers, no spoilers, I promise. I just want to hear your opinions on what you think.
Well, I guess who here's watched it? I mean, raise your hand.
Yeah, I mean, I've watched it. Who else? Nick, yeah.
Lauren and Nora holding
It's
out.
on my list. It's on my list.
Okay, no spoilers. So Nick, you've seen it. What do you think?
I don't wear that much corduroy.
I
I mean, that sounds like a you problem.
actually have a lovely corduroy sports coat that I enjoy wearing from time to
Oh,
time.
there you go. Does that pair nicely with your New Balances?
Yeah, I'm more of a oh my, why can't I remember the name of my brand of my shoes right now? The ones that have a really wide toe box. What are they called?
Vibrams?
No, Vibram is the sole.
Oh, that's okay.
Yeah.
Just look down.
I'm not wearing them. I'm wearing my nice office shoes now. I just got out of a board meeting.
Sneakers
I see.
allowed.
No, it's really funny. Why can't I mean, this is like the perfect time to like be an advertisement for some like shoe company. I can't even remember the name of the shoes that I use for running, but
It's a good game. What, Merrill, Nike,
Nope.
Adidas?
no.
Brooks? I
Nope.
wear
Hoka,
Brooks.
Asics.
No, man. Why can't I remember this? They're right
Good
next
question. What kind of shoe are you wearing?
Oh my gosh,
Like,
they're right
serious
here, right here.
off-brand?
There you go. No, I really am like gonna do this. They're ultras. I love these shoes. The ultra. There you go. That is some free advertising from Wyoming Stargazing. Love my ultra running shoes, even though I couldn't remember the name just a few moments ago. But there you have it. I've been thinking about budget numbers and that kind of thing, not running for the past couple hours. Okay, so Nick, your only comment is you don't wear that much corduroy. Nothing else, huh?
You know, well, yeah, there's the obvious of like maybe we should be doing a little bit more about climate change. That would be nice.
Yep, I like that. That seemed to be what the social commentary was pointing towards in that movie.
Yeah, there's some hints here and there.
There are a couple hints.
It's
Yeah,
really subtle.
yeah.
You really got to watch it a couple times to pick up on it.
Super subtle. No political commentary either.
No, not at all. No, they're above that clearly.
Yeah. And so Lauren, Nora, Danny, none of you have watched it yet?
I've seen it, but I want to suspend any comments until everybody's
Okay.
seen it, and then maybe we can pick it apart, all of us together.
All right,
All
there
right,
you
well,
go.
let's-
Lauren and Nora,
yeah.
your homework for the next couple of weeks.
Yeah, you gotta watch.
That's my
Don't
arm
Look
to
Up.
watch a Meryl Streep movie, you know. Like,
I
gotta do
know.
what I gotta do.
I loved her as president. I will say I thought that was a treat. And yeah, there's some special scenes with her. It's pretty awesome. Okay, so no spoiler alerts. Nothing else. My opinion is that it's definitely worth watching, but it's not really a sci-fi movie. It's really a political social commentary movie, which is fine. But yeah, I would not put it on my top 10 list of sci-fi movies. Let's just say that.
Yeah, and I guess there's if you're big fans of the Subaru telescope, there's a feature there.
That was pretty cool. Yeah,
Yeah.
they got a nice
Yeah.
a nice mention.
Yeah.
Yeah.
I was trying to think there was. Oh, that would be a spoiler. We'll have to talk about that next time.
All right, we'll talk about it next time. But,
Mine are astrophysical detail points that are irritating.
yes. Yeah, we can pick that apart. That'll be fun. Yeah. Well, we kind of strayed from astronomy history, but that's okay. Did anybody have any interesting tidbits or comments about any of the other historical facts over the past week or two of January that you wanted to bring up?
Well, now next year it's going to be easy, right? Now Christmas, right? The launch date of JWST. It's a new holiday.
I know, right? It should be a national holiday, right? I mean, we're talking 30 years in the making. I actually thought that was the most poignant thing that that Matt Greenhouse said several weeks ago during his presentation on the Cosmos Show, that he's been with NASA for 30 years, and the only project he's worked on is the James Webb Space Telescope. And everything is going perfectly so far. I think the The reflective shield is almost like fully assembled. The secondary mirror is coming out soon.
It's fully done. The sun shield
It
was
is?
finished
Okay.
up today, and they're starting
Sweet.
the secondary mirror tomorrow. So
That is
yeah.
so awesome.
I was like so worried about this whole thing. I was like, I know it's not out of the woods yet, but that was such a big thing to get done.
Totally. I mean, if anything was going to like rip or malfunction, it was probably the sun shield. So the fact that that is opened up.
Yeah,
and
I mean, they were having a lot of issues with it here on Earth, so it's pretty impressive that they got it all to work out there in space.
Yeah, agreed. Yeah, I am really excited about it. I got up at 4 a.m. to watch the launch and saw that epic moment when the solar panel unfurled with like the Earth in the corner of the field of view. Like, I don't know if they planned that like that or what, but that shot I think is like historically will like rival Earthrise, you know, from whatever Apollo mission that was. I can't remember now. We just talked about that the other day, but yeah, that was a epic shot. So yeah, we'll be talking about that one again. And yeah, we'll definitely keep you up to date on what the James Webb Space Telescope is doing, because that is kind of like the new kid on the block right now. So pretty good stuff. All right, well, you are correct, Nick. We will definitely have that in important dates in the history of astronomy, Astro 365 next year. But I guess if we don't have any more comments about that, we'll go to our break, and we'll come back in just a few minutes with our special guest, Claire Gorman. So don't go away. Come on back in a couple of minutes, and we'll see you then. All right, welcome back, everybody. We're here with our special guest, Claire Gorman, a PhD student at Cambridge University in the Department of Earth and Space Science. Claire, thanks so much for joining us this evening.
Yeah, thanks for having me.
Yeah, it's our pleasure. So we like to start all these conversations off with the same question, which is, what's the one question that you wish everyone would ask you, but nobody does?
Yeah, I think I would say the question is, do you want to co-author a paper with me where the
Nice.
only responsibility is to make beautiful figures?
I like it.
The answer is yes.
Nice. Well, hopefully someone will ask that to you soon.
If you're in the audience and you want to co-author a paper with me.
I hope we get lots of emails about that tomorrow. Oh, that's excellent. Well, tell us a little bit about how you got to studying what you study and how you ended up at Cambridge.
I guess I ended up at Cambridge because it's the only offer I got, actually, for PhD admissions. They're all very random. I applied to maybe like a dozen programs. The only one I got into was Cambridge, so there you go.
Wait, sometimes that's just how the cookies crumble.
Yeah. Why I got into what I'm doing is, I think I don't know, in my undergrad when I was studying Earth system science, and I got really into Dune, and then there's this whole, I mean, like Dune is obviously very famous now. It was like, it's still famous, but maybe slightly less so like 8 years ago. Then there's this whole like appendix where they talk about the like planetology of Dune and like how they'd go about kind of changing the climate from one stable state, which is like the desert world, to another stable state, which is like more like what you think of Earth as. And then I think I just got really obsessed with that. I was like, is this actually like something that real people research? And I kind of started doing it myself a bit. So yeah, that's it.
That's awesome. I love that. Very, very cool. And so where are you in your PhD program right now? What year are you in?
Yeah, I'm in my third year right now. In the UK, it's usually like 3+1 years, or like 3+1/2 year. Yeah, which I think is different to the American system. Seems like, where you kind of, most people there, you would not do a master's, right? You just go straight into undergrad, or straight from undergrad into like a 6-year program.
Yeah.
Yeah. So good luck to anyone that's doing that. But, yeah. So I've just submitted the first paper from my the PhD project that I kind of signed on to do. So that's exciting, because at first I thought it wasn't going to go anywhere and no one was interested in what I was doing, but it turns out that it's okay.
Sweet. Well, I would love to hear more about what you study, and I know you got some slides for us to take a look at. And so yeah, tell us all about what you're studying.
Cool. Should I do my spiel?
Yeah, go for it.
Okay. I can't see the what's on people's screens right now.
Yeah, you can just when you're like, you know what your first slide is, and when you're ready to go to your next one, just say like next slide, and it'll happen for you.
Cool. Okay. So I study exoplanets. What are those? Well, actually, maybe we should have dress rehearsed this, because there's some like transitions where you just press, whoever is doing this, I think you can just press enter until it makes sense. But so what are exoplanets? So every planet orbiting another star outside the solar system is an exoplanet. And we think that statistically, all stars should have at least one planet. So that means that there's billions and billions of planets out there in our galaxy alone. And we've managed to detect 4,500 of these. You can press enter now. And with better technology, this number is expanding rapidly. And what we're starting to do with this very large sample size is to build a picture of the whole kind of demographics, what planets nature likes to build. Answer. And because there are very few things we can measure for individual planets, we need to complement this work by using the knowledge base that we built up over centuries of looking at nearby solar system planets in much better detail, especially looking at Earth, which we've been observing for millennia. So to get a general theory of how planets work, we need to combine all of these branches. And that's why geosciences and exoplanetary sciences need each other. Next slide. So I think a good way to illustrate this is to look at every known exoplanet with a measured mass in terms of the distance from the star. And if there isn't like a scatter plot in front of you, then keep on going until there's a scatter plot with some blue dots.
Yeah, we got it.
Okay, cool. And then if you go one more forward. And then if you add solar system planets to this plot, it looks very different, which is what made the first exoplanet detections really confusing and hard to explain. Although there's certainly some observation bias, we also know now that most planetary systems around other stars are architecturally quite different to our own. One feature of this plot that stands out is that there's loads of exoplanets in between the size of Earth and Neptune, and these don't have any solar system analogs, unless Planet 9 is real, as we have been talking about a little bit today. So I personally hope it's real, because then we can go to it and measure it really well. So most of these kind of super Earth so-called exoplanets are very alien. Their nature is a burning question in exoplanet science. And in particular, because we're vain about these things, we're really interested in how similar they are to Earth and what parameters of habitability do they have. So you can imagine either a scaled up Earth, so that's something made mostly of rock and iron.
Recording in progress. Recording stopped.
Rock and iron with a thin atmosphere, or like a scaled down Neptune, just surrounded by a thick envelope of hydrogen and helium. And the general question is, how do certain properties of a planet scale with its mass? So as planets get larger, is it more or less likely that they have plate tectonics, or that they have volcanoes, or that they have oceans? So my research focuses on how processes that create topography scale with mass. Now you're looking at a slide that just says what my work is. I don't know if that's where we are, but well, why would someone want to do that? Well, for a planet with surface liquid water, the peak topography determines the capacity of ocean basins. So if I'm a planet with lower topography, I can hold a lower mass fraction of surface water before I'm completely flooded. And having both land and oceans is something we're looking for when we say Earth-like planet. Astrobiologists would say that both continents and oceans are required for surface life, so we can expect planets on either end of the spectrum to be in a very different planetological regime than Earth. Now we should be on this slide that's like 2 illustrations of plate tectonics. This is, can we model it? So the other thing we need to consider is that we are dealing with a tractable problem. So does that mean is the height of topography something that we can physically model? And on top of Earth's topography being complex, we can't assume that all processes on Earth are happening on other rocky worlds. We don't know if plate tectonics is operating to build up huge mountain chains like the Himalayas. And we can predict the most basic type of topography on the planet by simulating mantle convection and calculating what's called the dynamic topography of the surface. So the mantle of a planet is a solid rock, but it's still convecting on billion or million year time scales, just like the atmosphere is. So the mantle convection is a process that we can be nearly sure is happening on a planet, unlike plate tectonics. so if you have some plume of the mantle rising up because it's hot and wants to go up to the top of the mantle, then it's actually going to make a bump on the surface. So this is something that we see on Earth and we see on Venus and Mars. And it's a way of making topography on a planet that you don't need to have plates or anything really complex at all. It will just happen naturally because the mantle is convecting and pushing up the surface or pulling it down. So from these simulations, we can generate synthetic topography on planets. So now we should be looking at a slide that has some maps of longitude and latitude elevation that are all completely fake. It's just topography that I generated for arbitrary planets. But all these maps are for identical planetary conditions and therefore have the same root mean square elevation. So the point is we can generate these, and even though they're we're not saying that this is actually like the map of the surface of the planet, statistically, or it has the same statistics as the elevation of the planet. So that means it has the same mean or root mean square elevation and the same spread of elevations, like the same kind of histogram. So then we can integrate these maps from the surface to the highest point, and then that will give us the volume of the ocean basins. So what we can do is apply these models to real rocky exoplanets because they're hard to detect. And we only have a few examples. The best, probably the TRAPPIST-1 system, which is aptly named by Belgians. And we found that it's quite likely the water contents of these planets is too high for topography, for dynamic topography to sustain any land above sea level. Or actually even for the theoretical maximum topography, which is when the rock, or when you have a mountain that's so high that it crushes under its own weight. That's probably still not high enough to bring the land above sea level for the current estimates of the water content on these planets. But the takeaway is that we're starting to be able to build deterministic geophysical models to make predictions about the surface character of planets. And that's just the start, and very exciting about being in this field and getting to share it with all of you. That's my bit. Thanks.
Sweet. That's super cool. And I guess with kind of some of the new telescopes coming online, there might actually be a way in the next 10 or 20 years to actually observationally test some of these predictions.
Yeah. Yeah. With James Webb wouldn't be able to do this, but further down the line, and I think James Webb is kind of demonstrating the technological feasibility of some of these things. But the kind of next NASA flagship mission, which hasn't been confirmed yet, but they are kind of, some of the proposed missions would plan to be able to do something called direct imaging, which is something that we can do now for like really bright planets. This is where you can spatially resolve a planet from its star, where like normally you can't get that kind of like spatial resolution for like or the kind of spatial resolution and the brightness contrast that you need to differentiate a planet from the stars orbiting. If it's all the light that you're getting from the planet is just what it reflects off the star, it's not hot enough to kind of have, you know, the thermal infrared radiation. And this seems like one of the only ways to identify the surface properties of a rocky planet. I mean, there's kind of indirect ways that you might be able to say something from like some atmospheric chemistry, but that's all, it's so complex and there's so many different processes that would lead to the same chemistry that we observe that it's, yeah, I mean, like not to kind of hate on that because that's really important to do as well. But I think the directly imaging rocky planets, which is something that we might be able to do with a big telescope capable of direct imaging that's in space in like the 2030s, where you might be able to, I mean, you still won't get like a picture of the planet, right? Because it's still going to be one pixel. Yeah. But there's some really sneaky ways of kind of Because if you kind of are like looking at the planet over time, you're seeing a different face every time you look at it. So there's sneaky ways of kind of saying, oh, what fraction of this dot is land? What fraction of it is ocean? You can kind of say, because we know that water and land reflect differently, then it's possible. Like it's kind of been, there's the theory is there that we might be able to do this. It hasn't been really proven technologically yet, but yeah, pretty exciting prospects.
Yeah, I mean, I guess everything is impossible until you do it, right?
Yep.
Fortunately, humans have a pretty good track record of that.
Yeah.
Well, any questions from the co-stars or comments or anything else for Claire?
Yeah, this is really interesting. I always love seeing more of the geoscience side of exoplanets. I'm just curious, you mentioned that we learn a lot about planetary science, obviously from planets in the solar system. Are there planets in the solar system that have this kind of, I forget what you called it, but not plate tectonic topography?
Oh yeah. I didn't say the name yet, but it's called the stagnant lid regime, stagnant lid, and yeah, I mean it's basically just the opposite of plate tectonics. So I mean, there's like it's kind of a continuum, really, if you want to be kind of precise. But like the kind of simplified picture is you have a planet that's just like a one crust, single plate, and you might have some mechanism where you can kind of crack it and then turn it into multiple plates, and that's what happened on Earth. And there's a lot of like this is a pretty active area of research right now, which makes sense because plate tectonics like kind of creates a completely different regime for like the whole climate of the planet. This is what, without plate tectonics, you don't have a way really of bringing material from the surface into the interior. There's some kind of weird small scale processes, but like it's completely different. And a lot of studies on habitable planets will often assume that plate tectonics is operating, because it's really unclear if you can even have like the same kind of carbon cycling and water cycling without plate tectonics. But I think that's like a completely different question. It's really interesting to say, like, can stagnant lid planets also be habitable? It might look very different. We don't really know the answer. But to answer your question, yeah, Venus and Mars both kind of look like this because they don't have plates. I mean, people used to look, when we first got images of like the surfaces of Venus and Mars, people used to say like, oh, well, this kind of like feature looks like it similar to these features on Earth that were caused by plate tectonics. So like maybe there's plate tectonics, or maybe there was in the past. Honestly, we don't know. we have so little data, especially on Venus. We haven't been to the surface of Venus since like the Russian things in the 70s. So like, I mean, I think now
we're going back there, right? Will that data help us
learn
more about that sort of stuff?
I'm really excited about looking more at Venus. I think that will tell us a lot about Earth and about other planets in general. Yeah.
I was wondering, is there like a size limit to the size of the mountain you can create with this alternate plate tectonics, the convection? Can you form mountains as big, or is that like an indicator of might be one process or another?
Yeah. Or I should say it's not like the dynamic topography that it's called still operates on planets with plate tectonics. Okay. It doesn't matter. All you need is that the mantle convex. Mm-hmm. So mantle convection will happen as long as the planet is kind of big enough to be a planet. Like on Mercury, I think Mercury might just be a bit too small. Mm. But also Mercury is weird because it has like a massive core, right? Like its core is like 70% of like the whole radius of the planet, or maybe even more. I think 70% of the mass, even more of the radius. So like it just doesn't have enough scope for convecting. But for kind of most planets, like Mars, for example, so the mantle is convecting, and basically the height of this dynamic topography mostly depends on how vigorous the convection is.
Mhm.
So if something is just like, it's kind of a difficult term to quantify. Like we use like a kind of non-dimensional Rayleigh number to explain what the vigor of convection is, but just like if it's, you can basically think about it as if it's kind of strong. Yes, the convection is strong enough to support this, but for more vigorous convection, you would have smaller dynamic topography. And the explanation for why is still a bit tricky. No one is, or it can get very technical also, so I won't really get into why, but I think it might be like a more appropriate question to just ask about topography in general on planets and like how that scales with mass, regardless of whether it's kind of dynamic topography or like plate collisions or building material onto the surface from volcanism. And the answer is that it just scales with the inverse of the gravity in general. So that's why on Mars you have like 20-kilometer volcanoes. Mars is like 1/10 of the mass of Earth, so its gravity is also a lot less. And that's just because like per kind of unit mass of mountain, it weighs less. So it's just kind of easier for the crust to support it, and the deeper mantle to support it as well. So this is a really interesting question as well, because there might kind of be an upper limit to mass of a planet where you just don't have topography because it's all smoothed out just because the gravity is so strong. Like you can picture, you know, like something super dense like a neutron star, which is going to be essentially like a perfect sphere. Like topography will be like micrometers or nanometers. I don't know.
I got asked that question in my candidacy exam. And the guy who asked it was my professor for the class where we had that as a homework problem, and I couldn't remember. But yes, it's true. You can do the math.
Yeah, you can definitely do the math.
Yeah, I mean, it seems like there's a lot of range between like a super Earth and a neutron star, where you can imagine a pretty big planet that might have some rolling hills.
Yeah.
Are these like similar to the processes that would be happening in like an icy mantle? I know you couldn't have liquid surface water, so that's a different question, but
yeah, that's a great question. I don't know if anyone has looked at specifically the dynamic topography of an ice shell on top of like a liquid water mantle, but from a modeling perspective, it would be the same. Like you would just replace the material properties of the silicate rock with material properties of ice, and like these are very well measured things. You know, there is a bunch of work on kind of geomorphology of icy moons, and there are lots of parallels, because it is just material kind of it will behave like rock, I believe. Depends on what time scale you look at, but you still kind of have this behavior where it will flow right on long time scales and kind of brittly crack on short time scales. Yeah, no, I think it's actually interesting, because I wonder if you can kind of use that as another data point, as a kind of analog. I don't know.
Yeah, I'm thinking of like Titan, right? Which
Yeah.
definitely has lakes. So it has
Yeah,
some
yeah.
sort of topography to it, but whether it actually has, you know, bigger mountains than Earth or something. I'm not
Yeah.
sure. Yeah.
I mean, that information is on the internet somewhere. Like the height of topography on Titan.
Yeah.
But yeah.
yeah, I think it's fascinating with the icy moons that it's like what we think of as like rock is basically what the ice is
Yeah.
on Icy Moons.
Yeah, no, but so much of it is completely analogous. Yeah, and I think I remember seeing someone made like a figure of like the maximum, like the difference between the maximum elevation and the mean radius for the different moons. And I think you do kind of get the same kind of pattern as you do for like the three rocky planets minus Mercury, which barely counts as a planet. But
That's always fun when you have a theory and you apply it in a slightly different way and it still works.
yeah.
Yeah, it seems like something's working when that happens, right?
Yeah.
Science.
Right? Nice.
Claire, oh, sorry.
Oh, go ahead. No, go for it, Annie.
Yeah, I was just going to ask, I'm curious. So granted, my background is medicine, as the rest of these guys know, and this is very, very far. What you've just presented is very different from what I'm, used to studying. And I'm just curious how you landed on this particular topic as something that you wanted to investigate, and what you see, where you see taking this after you graduate, aside from
the
publishing.
Part, I don't know about.
Okay.
Yeah, I mean, the second part where I can take this after I graduate, I think just depends on where money is, who wants to pay me to do more research. The first part, I mean, it was just something I kind of, my PhD supervisor and I came up with while I was applying to the program. I mean, just like the details of like, because different application processes are different. But the one I did was you kind of had to have a project beforehand and you start immediately. I know there's like some US schools where like you kind of do like a interim year of doing general stuff first, and then you don't do the research until later. Well, I think it's just topography is worth studying because there's a massive literature on it for like the solar system planets, because that was kind of like a big focus of like 70s and 80s kind of research when we first started having kind of good quality data from space missions. And people started like, when you like, imagine if you're like a scientist in the 70s seeing like photos of the surface of Mars for the first time, and like no one has ever seen that before. And then we're like, oh my God, like what is that feature? Like it looks just like this one I know in like Colorado or whatever. And like and you start thinking about like how that was made. And like, so those people did loads of work kind of like prepping me. So all the theoretical basis of like this surfaces of planets is kind of laid out based on the solar system. And all I have to do is kind of apply it to a more general case, or like how would that be different, say, if the mantle had more magnesium in it, or which sounds kind of like a random parameter, but turns out to be very important for like the whole flow of the mantle and all these kind of thermodynamic properties that govern mantle convection. So yeah, that's
Thank you.
So Claire, this question's maybe hard to answer, but I guess that's kind of the point, right? That's why we have questions. So I'm just thinking of like the 4,000 or so exoplanets we've discovered so far, and probably the tens of thousands that we'll discover in the next 10 or 20 years. Do you have a hunch on what the breakdown is going to be with planets that have plate tectonics versus not?
Yeah, that's a great question. I think it's honestly like we don't have enough data points to say anything about that, because we know like 3 rocky planets that have mantle convection, like Mercury. The reason why I say Mercury doesn't count, like I believe Mercury is a planet. I'm not trying to say it shouldn't be a planet, but just because its mantle is kind of too weak to convect, it doesn't have the same kind of geodynamics as what we think of as a planet. So it's kind of dead. You know what I mean? Like it's just there. It's not really doing anything. It's getting bombarded by craters, but that's about the most interesting thing. So we have 3 planets. One of them has plate tectonics, the other 2 don't. So like the problem is trying to say anything about the universe from this. I think that or my hunch, which I want to really underline as a hunch, is that for plate tectonics to happen, you need to have something kind of click that depends on a bunch of conditions all falling into the right place. And it might not even be that this is a function of the bulk properties of the planet. Say like if my planet has this mass or like this density or kind of this water content, then like any planet that has those conditions will always start to operate in the plate tectonics mode. There's a scientist named Adrian Lenardic that works on this a bit, some kind of stealing some of his ideas. But I think that it requires something kind of special, and it's really impossible to say how likely it is that these conditions happen at one time. But I think I can't say like a number, but I do think it's on the rare side.
Cool. I mean, that's the best answer I've ever heard. So
yeah, I mean, like I think Archean Earth, which is like the era of Earth's history 4 billion years ago, we don't even know if plate tectonics happened then. Like it's been really like every few years it seems like there's a new Nature paper saying like, oh, we found when plate tectonics started, but like it's all kind of, I don't know. No one really knows. But it does seem like the consensus is that Earth started in this kind of stagnant lid mode, and then at some point something happened where the crust was able to break up properly, and then now we have plate tectonics. But we don't know how this happened. But I think the fact that we think Earth was originally a stagnant lid planet makes me think that that's kind of naturally what happens. And then if the conditions are there, then yeah.
Can it go the other way? Is like a future Earth gonna go back to stagnant lid?
Yeah, I mean, we don't know, but there's no theoretical reason why that's impossible, I think. So yeah. And that would have like all these cascading consequences for the whole planet. Like it's a massive factor, and it's really hard. I think, I don't want to say impossible, but like very, very unlikely that we'll get data that kind of tells us if an exoplanet is in the stagnant lid mode or the plate tectonics mode, unless someone has an amazing idea. Like it's quite tricky.
I'm going to wager that someone will have that idea.
Yeah.
So, I will be willing to bet on that. I don't know if it'll be in our lifetime or not, but
yeah.
I think someone will get there. I'm just remembering right now that the Jackson Hole Geology Club is actually having their meeting right now. Wow. And I'm going to send them the recording of this talk so they can listen into what you had to say about plate tectonics. I think they'll find it incredibly fascinating. I definitely do as well.
I had another question, if that's okay. Now that you're making me think about the old Earth, it's making me think of this idea of Pangea, of there being one landmass. And I'm wondering how that also fits in with this model, because I'm remembering your synthetic topography and it looked pretty like uniform across the latitude and longitude. And so why would there have been this one landmass and then everything else filled with water, as opposed to it being more randomly distributed?
Yeah, I mean, for dynamic topography, which is the one that's only kind of showing the mantle plume. I mean, because that literally is just a reflection of where the plumes are. So like mantle I mean, like Mars is an interesting case, because I'm not sure if you're familiar with like Mars topography, but basically you have like Olympus Mons, which is like the biggest volcano in the solar system, like dominating this whole one hemisphere, and the other hemisphere is just plains. Okay. So like you have this really weird structure. It's not quite Pangea because it I mean, like it's formed in a different way, but I guess it's the same like
Idea.
visible
Yeah.
effect, right?
Right.
So for dynamic topography to create this kind of like single continent vibe, you would need to have just like one massive plume of upwelling mantle. And then so it kind of goes up one hemisphere, it goes around and like down
Right.
back to the core on the other side. And this is actually something that models of tidally locked planets will find. So that's like when a planet is really close to its star, that it's basically like the moon and earth, where like one face is looking at the star the whole time and the other face is looking out into night the whole time. And because of the way that like the like temperature differences are between the night side and the day side, you can have these kinds of regimes of convection where you have like one upwelling plume on the day side underneath the sun. And that would, in that case, you'd have like one kind of big continent of dynamic topography. Or it's, I mean, like the term continent is like, I don't want to use that because it's specific to Earth. We don't really know. Yeah, it's kind of more complex. But for, yeah, you can make one like big swell of land under the sun. And then the rest, if there's water on the surface, then we kind of fill in the basin on the other side.
Yeah.
Does your TRAPPIST model take that into account? Because I believe the TRAPPIST planets are close enough.
Yeah. I mean, for the TRAPPIST model I was doing was just saying the just the peak topography you could have for any case that's just based on the strength of rock. And yeah, like I'm not, for the dynamic topography model, I haven't done this mode of convection where it's called like degree 1 convection. It's when you have like kind of one plume. And that's a great question, actually. I don't know if that pattern of convection would change the relationship between the height and the convection. So
do you have rotation in your model at all?
No, yeah. I mean, you don't, at this level, you wouldn't have like Coriolis forces coming into play. That would matter for like atmospheric stuff. But I think the time scales are so short, or so long, I mean,
that makes sense.
Yeah, it's not. Yeah, I mean, I haven't like thought about it really, but it's never something that mantle modelers do. So I just assume that at one point someone kind of did the calculation and found it didn't matter.
Makes sense.
Yeah, no, but I think it would be a great project to do this for like a kind of tidally locked planet, and then say if that made a difference for how much topography you can build. Yeah.
Well, it sounds like Nora will write the paper if you'll get the figures.
Yeah.
This is way outside my comfort zone. I model planets as point masses, all right? This is all way more complexity than I need.
That was a nice connection though, Nick. Nice for bringing us home there. Well, you got your wish, Claire. Somebody almost asked you that question. Well, we're about out of time. This is really fascinating. I could keep talking about this for a while. Are there any other questions for Claire from any of the co-stars? Claire, any final remarks you want to leave us with?
I think that if you want to study planets, I think that you should do Earth science. I mean, like, there's lots of great astrophysicists that like started in something else and went into planets and are doing great and are really contributing a lot. But I think that we also need lots of Earth scientists that really kind of are trained in these specific processes. And then that's, yeah. Actually, we just need everyone to be doing everything.
Yeah, I mean, it seems like there's an awful lot of overlap in planetary science and room for both expertise to collaborate and get things done.
Yeah.
Well, thanks for that. And thanks so much for joining us this evening. It's been a pleasure chatting with you. And I really appreciate your time. We've got a thank you gift for you. And Maggie, I'll reach out to you to get that taken care of. Thanks to all our co-stars for being back here with us in the new year. Psyched that it's 2022. We'll be back in a couple weeks with another awesome special guest and conversation about astronomy. Thanks to all the folks behind the scenes that make the Cosmos Show happen. Our stream master, Gavin, of course, Maggie, Wyoming Stargazing Board of Directors, and all of you out there who are watching. Thanks so much for joining us. And we'll be back in a couple weeks. Until then, enjoy and don't forget to look up. We'll see you next time. Bye.